Okay, so let us start with what we ended yesterday. So if you recall, we were into like when the roots of the characteristic equation, this is equal to 0 for the system of equations. Of course, we are still considering linear system of equations. I mean, given by this, and of course, this characteristic equation is nothing but this equation, as you can see. And I had assumed that my matrix A is given by A, B, C, D, and here now is the trace of this matrix, and delta is the determinant of the matrix A. Okay. And then yesterday I had told you about the very first case when we were considering real roots, and we were considering firstly distinct real roots, and we were the first case we were considering when both the characteristic roots or both the eigenvalues lambda 1 and lambda 2, they were negative, right? And under all circumstances we assume that lambda 2 is less than lambda 1. Okay, and when both lambda 1 and lambda 2 are negative, so I can write this as this. And yesterday I explained to you that the general solution, I can write it like this, and I can adjust it like this one. I can adjust it like this one, and you can see that your lambda 2 minus lambda 1 is always going to be negative, right? From here itself, you can see that lambda 2 minus lambda 1 is always negative, right? So, irrespective of whatever may be the sign of lambda 1 here, you know that as you let t tend to infinity, this term here, it is always going to approach 0. Is it okay? Fine?
Yes, sir.
Right? So that means the vector k1 is going to dominate the solution. Okay. So if t tends to infinity, from here you can see that here you can see that x is going to tend to your c1 k1 into the power lambda 1 2, right? So this bigger eigenvalue that is going to dominate the solution. Okay, and yesterday I had already shown you how to draw this vectors, and again today I'm going to take another example later on. So even if you haven't understood it clearly, it is going to be clear to you later on. Okay, and then I have told you that if I want to check the property of the critical point 0 as stable or unstable. So here you can see that k1 and k2, they are the basic vectors here, right? And you can see that k1 is the dominant vector. Okay, so then you should always remember that if c1 is not equal to 0 and c2 is not equal to 0, right? The linear combination of the other vectors are always going to give you curves as your trajectories. Okay, and in this particular case, what is going to happen when both lambda 1 and lambda 2 are negative? Like all the other curves, they are going to spiral. Towards the critical point 0 here. Okay, and yesterday I had explained to you that this curve, what is going to happen at the point 0? Their tangents are going to have the slope determined by the entries of the dominant vector k1, and the slope here you can see that it is given by k21 by k11, right? So here you can see that they are all, I mean, converging towards the origin 0, right? So now can you tell me the way I have drawn the figures, like the origin will be what? That is going to be a node. Okay. So this type of trajectory, when they approach some critical point, so this critical point is called a node. I mean, when they approach, or they can run away from the critical point as well, right? So in those situations, whenever there is something is converging towards a point or diverging from a point, right? That point is called a node. Okay. And here, since it is converging, we are going to call it a stable node. Because here you can see that it is again coming back. Although you start at some different initial points, the trajectories are coming back towards the critical point 0. Okay. Now, similarly, when both lambda 1 and lambda 2 they are positive, when both lambda 1 and lambda 2 are positive, so then what is going to happen? See, both of them are going to be positive. So then I am going to have the same situation. Now, if you look here, then what is going to happen? Like as t tends to infinity, my solution vector x bar, it is going to approach c1 k1 e to the power lambda t. Now, when t tends to infinity, because lambda 1 is always positive, this is going to go towards infinity. Is it okay? Right? And here, the situation is similar to the previous case. The only difference is that now the orientation of all the trajectories, they are going to reverse. So basically, what is going to happen? All of them are going to move away. This origin. Okay. So in case 2, case B, so this point 0, it is called an unstable node. Okay. Is it okay with everybody? Yes. Okay, fine. So now,
hello, sir. Sir, what is your definition of stability and instability?
Just a minute. I think I'm not hearing the sound clearly. Yeah, can you repeat your question?
Sir, what is the definition of stability and instability here?
Like say, the way I told you yesterday in the example where I explained to you the notion of asymptotically stable, right, and unstable equilibrium point. So whenever something is converging towards the critical point, we say that it is stable. If it is diverging away from the critical point, we say that it is unstable. Okay, so I still haven't given you a formal definition of asymptotically stable. Although yesterday I told you that, okay, this is asymptotically stable, right? That I'm going to do in my next class when I'm going to consider linearization of nonlinear equations. Okay, so for the time being, what you should remember is that whenever the trajectories are converging, it is stable. When they are diverging, it is unstable. Is it okay? Fine.
Okay.
Now, let me come to the case. I'm still in distinct real eigenvalues. Case C, when lambda 1 and lambda 2 are of opposite sign. Okay, so that means we are going to assume that your lambda 2, this we are going to assume that. Is it okay with everybody? Fine. So now, then what is going to happen? Just now you concentrate. Now you concentrate on this solution. Now you concentrate on this solution. Okay. And again, let me just erase this. Just a moment. Okay. Okay. Let this remain. Okay. So now, if you look at the solution, then again, this statement, as t tends to infinity, you know that all the solutions are going to be converging towards this factor, kind of this factor. Okay, and it is going to be running away from the origin because your lambda 1 is positive. Is it okay here? Is it okay? Fine.
Yes,
okay,
sir.
let me try to explain it in another way. So firstly, let us assume that your C1 equal to 0. Let us assume that C1 equal to 0, right? So in that case, what I am going to have? In that case, I am going to have x given by C2 K2 e to the power lambda 2t, right? So C1 equal to 0 will imply your x equal to C2 K2 e to the power lambda 2t, right? In this particular case, what is going to happen? Because your lambda 2 is negative, that is why what is going to happen? If you draw the vector, K2, then what is going to happen? All the points which originates in K2, right? Suppose you are considering a trajectory starting on the line determined by K2. So then what is going to happen? They are going to have trajectories converging towards the origin because lambda 2 is negative. Is it okay? Fine. So then suppose this is my K1 and suppose my K2 is something like this. Okay. So for K2, what is going to happen? They are going to converge towards the origin. All the trajectories are going to converge towards the origin. Like say here, if you take any point here as initial point, then as t tends to infinity, it is going to converge to 0, right? And this is x, this is y. Okay, and this is K1. So now, okay, and similarly, you know that if C2 is 0, so then definitely my x is going to converge towards K1 e to the power lambda 1t. And in this case, if you consider this factor alone, then you will see that what all the points in this line, it is going to be diverging, right? See, always remember whether it converges or diverges, it is determined by the sign of lambda. Is it okay? It is determined by sign of lambda. Okay? If it is positive, it will diverge. If it is negative, it is going to converge. Okay? So now let us see the overall situation. Now you know that if I take a linear combination of the fundamental vectors, all the other trajectories, they are going to be some curve. Okay. Now you will see here that once t tends to infinity, all the trajectories move towards the dominant eigenvector k2. Is it okay? See, I still haven't drawn anything. I'm just making this comment. Based on this fact. Right? When t tends to infinity, definitely what? All the trajectories are going to be leaning towards the vector determined by k1. Is it okay?
Yes, sir.
Fine. So that is why what is going to happen? All the other trajectories, they are going to look like this. They are going to look like this. They are going to look like this. Okay. So similarly, see, they will not only be moving towards the vector k2, sorry, k1, the dominant eigenvector, but what is going to happen? They will be moving away from the origin as well. Okay, so what is going to happen? That this line determined by the eigenvector k1, it is going to act as an asymptote for all the other curves. Is it okay? Is it okay?
Yes, sir.
Right? So now you may be asking me. So maybe let me ask you the question. Now, can you tell me? I mean, why the situation could have been different? Why everything is moving? Everything is moving away from the point 0, but it is leaning towards the vector k1. Why it is not to k2? In fact, I have already explained it many a times. See, the answer lies here. Always remember, eventually, all the solutions are going to converge towards the dominant eigenvector. You should always remember that. Is it okay with everybody?
Yes, sir.
Right? So in that case, this critical point 0, it is called a saddle. It is called a saddle or saddle point. So is it stable? I mean, can I consider in this particular case 0 as a stable or unstable? Should I call it stable or unstable? Yes? Yeah, tell me.
The trajectories are not converging at this point 0, 0.
Yes.
So this must be unstable.
This is unstable. Here, the only stable trajectory it comes out is for this line K2. All are unstable. So just let me give you one example. So then all the concepts will be clear. Okay. Fine. Did I miss something? Yeah. I'm just one thing. That comment I made. I told you that all the other trajectories or all the other trajectories, which are nothing but curves, they are going to lean towards your K1. They are going to lean towards K1. But remember, not originating in this line. All the other trajectories not originating on the line K2, they are going to lean towards K1. They are going to lean towards this one. You should remember that, because if something is, if you take a initial point here, it is always going to move along this line. and it is going to converge towards 0. Okay, fine. So, okay, now let me do one example. Okay. So the your A is 2, 3, 2, 1. Where A is 2, 3, 2, 1. Sometimes somebody is trying to log in, I guess. Just a minute, let me see. Okay. See, I have been getting a warning there is that because of the network problem, some of you may not have been able to follow it properly. Is it okay? Like, is it okay with everybody? Can everybody see the blackboard?
Yes, sir.
Yes, sir.
Okay, okay, fine. Okay, so now because we have got smarter than before, so that is why I'm not going to, write down the characteristic equation as I used to do before. So you know that here the characteristic equation is lambda square minus tau. Tau is what? 2 plus 1, right?
Yes,
Is it okay? Right? Plus delta. Delta is 2 into minus 6, that is 4. Minus 4. So this is equal to 0. Or I don't even have to do that. So this is simply what? Tau. Tau is 3 plus minus tau square, that is 9 minus 4 into delta, isn't it? 4 into minus 4 divided by 2. That's it. I don't even have to do this. Okay? So this is 16 plus 9, 25. So 3 plus minus 5 by 2. So you are going to get lambda equal to what? 4 and minus 1, right? 4 and minus 1. Is it okay? Fine?
yes, sir.
Did I do any mistake? I should be fine. Yeah. Okay, fine. So now let us try to find the eigenvectors corresponding to 4. So corresponding to 4 eigenvector, if you want to find out what you have to do, 2 minus 4, that is minus 2, 3, 2, 1 minus 4, that is minus 3, right? Is it okay? Is it okay? This is simply a minus 4, right? Fine. And then this is, you know that this is going to be equivalent to 0, 0. Okay, fine. So the obvious solution K1, that is going to be equal to what? 3, 2. Is it okay?
Yes,
Yeah,
sir.
you guys are so silent. So similarly, your lambda 2 equal to minus 1. So then what I'm going to get? A plus sign, right? So 2 plus 1, that is 3, 3. Then 2, 2, right? So it is fine. So what is K2? This you have to give me the answer. I'm not going to do this.
1 minus 1.
1 minus 1. Okay, fine. So now, see, some of the concepts that I taught you at the very beginning, now probably that is going to be clear to you from this. No? That is going to be clear to you from this. Okay. So now, suppose I want to draw the face portrait. Okay. So then, what I'm going to do? See, firstly, what you do, you simply draw these eigenvectors. You simply draw the eigenvectors, right? So then, see, K1 is 3, 2. So it is going to be something like 1, 2, 3. Okay. It is going to be something like this. It is going to be something like this. Okay. I'll come back to this again. So similarly, this one is 1 minus 1. So 1 minus 1. So it is going to be something like this. Okay. So this is K1. This is K2. Now you can see that this line is simply y equal to what? 2 by 3x or 3 by 2x. Y by x is what?
2 by 3x.
2 by 3x. And this line, this is y equal to minus x. Fine. So far it is good, right? At least K1, K2, how to draw them, I know. Fine?
Yes, sir.
Fine? Okay. So now, let me try to draw K1 e to the power lambda 1t. E to the power lambda 1t. Okay. So now if you want to draw this K1 e to the power lambda 1t, now you know that lambda 1 is 4. This is positive, right? So that means here all the trajectories starting at some points on the line represented by K1, it is going to be diverging away from the origin. Is it okay? Fine. So that means it is going to be something like this. It is going to be something like this. Fine?
Yes, sir.
Okay. So similarly for K2, because K2 is associated with a negative eigenvalue, it is going to be something like this. Is it okay? Fine. And see, I told you earlier, at the very beginning, I told you about the roles of the constants C1 and C2. Now, just look at it. Say, suppose I take this combination. Say, I again multiply it by C1, right? So, I explained to you the concepts of half lines. So then, what is going to happen? If C1, say, consider your K1. If C1 is positive, my x and y, they are always going to lie in this first quadrant, isn't it? Are you getting the point? Right?
Yes, sir.
Right? They are always going to lie in the first quadrant. Okay. So that is why this part is going to correspond to C1 greater than 0. Similarly, this part is going to correspond to C1 less than 0. Is it okay? Fine, right? So similarly for C2 also. Fine. Okay. So that part we are done. So now we have to draw the other trajectories. Now you know that because this is the dominant part. Say this is the dominant part. So that is why all the other trajectories, if they don't start from any point lying on K2, they are going to move towards the line K1, I mean the vector K1 in such a way that the line represented by the vector K1 is an asymptote. So basically what you have to do, all the others, they are going to move towards this, like in this direction, in this direction. Similarly, it is going to be something like this. It is going to be something like this. It is going to be something like this. So you can draw as many as you can. So I'm just writing this. So obviously here 0, it is a saddle point. Is it clear now? Is it clear?
Yes, sir.
Right? Okay. So now let me, and again all the examples I have taken from Jiten. So you can again revisit it by going back to that. Okay. So now let me take another example. Say I am going a bit slow for this part because I know that although I mean they look very interesting and fascinating, but all those minor things sometimes I have seen that is not very clear to the student, and I want you to be very clear about it, because as I have told you earlier that we have some selfish agenda, because you guys are going to act as TAs later on. So I want you to go to your tutorial classes with clear concepts in mind. Okay. So now I am taking another example where A is -10, 6, -10, 6, 15 -19. 15 -19. Okay, so can somebody give me the eigenvalues? Yes.
-4 and -25.
-4
and -25.
-25. Okay, fine. So now, obviously, you can see that both of them are negative, right? So obviously, what we are going to get, we are going to get a stable node. We are going to get a stable node. So as before, what you do, simply find out now, say A corresponding to this, A plus 4i. So this is going to be what? -10 plus 4. -6, 6, 15, again -15, right? Okay, and you know that this is equivalent to -1, 1, 0, 0. Fine. -1, 1, 0, 0. So your K1 is very easy. Fine. Okay, and then A plus 25i. This is going to be -15, 6, 15, -19 plus this. This is again going to be what?
Is +15, I think first.
Because 25, right? -10 plus. So 15, 6, 15, 6. So eventually, obviously, this is going to be 0, 3, 5, this, right? So your K2, this is simply, it's up to you. 2 -5 or -5, it is up to you. Don't worry about it. Okay? So obviously, you know that this is going to be my dominant, eigenvector. Okay? So then, simply what you should do, you should draw K1, 1, 1. So this is fine. This is 1, 1 and 2 minus 5. 1, 2, 1, 2, 3, 4, 5. So it will be somewhere here. So I'm going to have something like this, right? And you know that because both the eigenvalues are negative, that is why I am going to have something like this. I'm going to have something like this. So this is K1. This is simply y equal to x, and this is K2. This is simply y equal to what? 5 by 2x. Okay. So now you know that what is going to happen. All the others are going to spiral towards what?
Origin.
Origin in such a way that I mean at the origin their tangents have slope simply 1, isn't it? Their tangent is slope determined by this line. Okay, so basically this line is going to be a tangent at the origin to all the other trajectories. Is it okay? Fine. So it will be what? It will be something like this. It will be something like this. I mean, it may be something like this, right? See, it should be such that I mean, it's spirals like that. Okay, I think this one is. I should draw it something like this. Okay, I should draw something like this. Okay, fine. So yeah, so you can draw as many as you can. So basically, they have to finish at the point 0 in such a way that this line is a tangent to the trajectory at the point 0. That's it is going to be like that. Okay, so for a better picture, you can just simply look at Jill and Kulen, or what you can do, you can use that phase plane, I mean script in MATLAB, and it is going to give you all the other trajectories. Fine. So we have dealt with, I mean, 3 cases. We have dealt with 3 cases. So now let us move to complex. I'll move complex. Don't worry. I'll go to complex roots later on. But before that, I have to go for what? Real roots, but what? Tell me.
Well,
Real, yes. Real roots
are equal.
Equal, yeah. Okay, fine. See, okay, just a minute here. Okay, I've summarized it out. Okay, so now let us assume that I mean both the roots are equal to lambda. Both the roots are equal to lambda. Okay, so then what is going to happen? I may have 2 subcases. Right? One is when you can find 2 distinct eigenvectors k1 and k2, right? Corresponding to the same eigenvalue lambda. Is it okay? Right? We have already seen, I mean, examples for that. Okay. So then your general solution, it will be simply is it okay with everybody? Fine. right? When you can find, two, distinct eigenvectors corresponding to the same eigenvalue lambda. This is this equation, fine? So now, again, what you are going to do, corresponding to your C2 equal to 0, you are going to get an eigenvector, not an eigenvector, right? I say you can get a vector along your K1. So similarly, by plugging in C1 equal to 0, you can get a vector along K2, right? So solution vector. Is it okay? Fine, right? So in that case, what is going to happen? So maybe I'm going to have, sorry. Rather, I'll put my y-axis here. I'm running out of colored pencils. Okay, fine. Say, suppose this is K1, this is K2. I still haven't given any arrowheads. Remember, I still haven't given any arrowheads. That I'll do later. Okay. So now the interesting part here is that if you look at this term, this particular vector given by say C1 K1 plus C2 K2, right? It doesn't depend on T. Isn't it? Are you getting my point?
Yes, sir.
Right? So their linear combination is going to give me another vector. Is it okay?
Yes, sir.
Right? Their linear combination is going to give me another vector. See, earlier what happened? I had something like C1 K1 e to the power lambda 1 t plus C2 K2 e to the power lambda 2 t. Right? So in that case, what is happening? So this particular part, again, it depended upon t. This particular part also depended upon t. Right? So that is why I was getting some curves out of this, right? But now this is still there. But it is simply just like a scalar multiple, isn't it? It is simply just like a scalar multiple. And that scalar multiple is going to depend upon the value of t, right? But what is going to happen? This vector is going to remain fixed, isn't it? Depending upon the values of C1 and C2, right? And whatever vector, say, suppose this vector, it looks something like this, This vector looks something like this. So now, depending upon what is the value of e to the power lambda t, right? It is going to elongate or contract. Are you getting my point?
Yes, sir.
Yes, right? So what I mean to say is that here, somewhere down the line, I am going to get a vector, say, C1 K1 plus C2 K2, right? And like say, and again, if you multiply it by interval lambda t, they are going to lie along the same vectors, right? And depending upon the values of C1 and C2, I can get all other vectors, but they are going to be along. All other trajectories, but they are going to be straight lines. Okay. So now, what is happening? What is happening? Now, I didn't tell you the what is the sign of lambda. So depending upon the sign of lambda, if lambda is negative, you are going to have this converging trajectories, and if it is positive, you are going to get diverging trajectories. Okay. So in that case, when again, see here, everything is converging towards a point. So this is a node. This is still a node. So this is if in case it is converging, like in case when lambda is negative. So this point 0 is called degenerate stable node. Okay. And if it is divergent, if when lambda is greater than 0, this is called degenerate unstable node. Is it okay? This is called degenerate unstable node. Okay, fine. So again, the word degenerate has certain meaning. I'm not going to explain it to you today. Later on, I'm going to explain it. This. Although I don't know whether that has something to do with the exact mathematical meaning of this or not. That I don't know. But there is certain thing associated with this. I'm going to explain it to you. Okay, fine. So this was case 1. So what about case 2? Case 2 was what? When you can find only what? When you can find only a what? Only one eigenvector corresponding to that one, right? So then, if that eigenvector was say k1, then your solution is going to be that c1 k1 e to the power lambda t, then plus c2 then k1 t should I write it? Okay, fine. E to the power lambda t plus your p e to the power lambda t, right? P e to the power lambda t, where you determine p from the equation a minus lambda I p. This is equal to k. Okay? Is it okay? Fine. So now, here we are going to do one particular trick. So can you tell me what that trick is going to be? Okay. So I'm going to get something like this. Is it okay? Is it okay? Fine. Is it okay?
Yes, sir.
Right. So now again, if you look at the expression under the parenthesis, right? Here their combination is not going to give you straight lines, isn't it? The trajectories, they are going to be some curves. Is it okay?
Yes, sir.
Right? It is going to give you some curve. Okay. And again, when your C2, when your C2 is 0, again, you are going to have all the solutions converging towards a vector lying along K1. Okay. So because of that, here it is going to like, if say suppose this is say K1. Suppose this is K1. So then if lambda is negative, so definitely I know that the trajectories are going to be something like that. Okay, trajectories are going to be something like that. So then what is going to happen? All the other trajectories, they are going to be something like this. And then similarly, it will be the opposite here. It is going to be something like this. It is going to be something like this. Okay? Is it okay with everybody? Fine? Okay? So,
Sir, is this the case?
it will?
Sir, is this the case when lambda is negative?
Yeah. This is the case when lambda is negative. Yes. This is the case when lambda is negative. Yes. Okay. Like similarly, if lambda is positive, the orientations are going to be in the opposite direction. That's it. Okay. Everything is going to move away from the origin pole. So now here also in both the cases, they are called, degenerate stable node, depending upon whether lambda is negative, or degenerate unstable node, depending upon lambda is positive. Okay, so here when you have equal root, again you can see that you are getting again nodes only. But what happens when you have two distinct eigenvectors coming out of the same eigenvalue? Then you get straight lines. Okay, okay, right, as your trajectories. Okay, fine. So that brings me to now complex eigenvalues. Okay. Do you recall the formula for the solution when we had complex eigenvalues? Okay. Okay, so suppose, let me assume that lambda is equal to alpha plus minus I beta. Okay, and then you know that this x equal to should I write in terms of x1, x2? Do you recall that? What was x1 and okay? Anyway, C1. C2, then for t, and where your beta 1 equal to so k was nothing but the eigenvector corresponding to alpha plus I beta, right? This is good enough for us. Okay, fine. Now, let us consider two cases here. Let us consider two cases here. Of course, case one or case A is when lambda is pure imaginary. When lambda is pure imaginary. Okay. So in that case, if you look at this equation, if you look at this equation of the solution vector, the general solution. So obviously, so that means lambda equal to 0, lambda equal to 0. So I'm going to be simply left with C1 into this and C2 into this. Are you getting the point? Is it okay? Fine. So that means I am going to have something like x equal to C1. Should I write not C? Sorry, let me not write C1. X is going to be something like, say, C3 cos beta t plus C4 sin beta t, and y is going to be something like C5 . Is it okay with everybody? Is it okay with everybody?
Yes, sir.
Right? Because these are nothing but B1 and B2 are nothing but real and imaginary parts of the eigenvector. So their entries are going to be some real numbers. That's it, right? So if you take combination of all of them, it is going to look something like that. Of course, here C3, C4, C5, C6, they are some real constants. Okay. So now you know that here by eliminating your sin beta t and cos beta t, this is going to give you what? This is going to give you the equation of an ellipse. Is it okay?
Yes, sir.
Right? So that means what is going to happen? What is going to happen? I mean, if you consider this critical point 0, so then if you try to find out any trajectory starting in the xy plane at some point, like say except this critical point, so then it is going to whirl around, or it is going to rotate around the point 0, 0 in a closed circuit. Okay, in a closed circuit, okay, in a closed circuit. Okay, fine. It is going to be something like this. It is going to be something like this. And in that case, this critical point 0, 0, it is called a center. It is called a center. It is called a center. Okay. Now the next part. So next part in Jiten Cullen, they are not very clear about that, but I try to rope in something here. Okay, fine. So case A is done. Now, okay, so in fact, I have gone through a couple of books for this next case. This next case is case B, where your alpha is not equal to 0, where alpha is not equal to 0. Okay, so then, like say in all the books, they will say that by looking at the solution this, looking at this solution, you can easily see, it is not very easy, that it is going to be something like this. It is going to be something like this. The trajectory trajectory is going to be something like this. Okay, and of course, depending upon the value of alpha, it is going to be converging towards 0, or it is going to be diverging away from this point 0. Okay, so I didn't find any convincing explanation. Like say for that, what you must have, you should be able to get an expression something like that, isn't it? Right? This is going to define a spiral. Is it okay? Fine? Isn't it?
Yes, sir.
Right? You should get you should get something like that. So Simon's book, I liked his. Simon's is the only book where I have found something which is kind of convincing. But one thing, it is still not very clear to me. I'll tell you what was not very clear to me. Maybe you can find it out for me. Maybe it was very straightforward, but I couldn't figure out. So now let me tell you one thing. Say suppose I am considering a point in the r theta plane. So then that means if I consider the coordinate, so that means I mean this is the distance of this point from the origin is r, okay, and it makes an angle theta with x-axis, right? Okay, so now if I want to track a trajectory, say starting at a certain point, so now it can have any shape. Is it okay? Right? It can have any shape. So now, if I consider it in the, although it is a xy plane, but if I consider it in the r theta plane, then this is going to represent a spiral if this theta for all the locus or for all the points lying on the trajectory, like if the trajectory is such that this theta is always going to be increasing, whatever may be the value of r, if it is always increasing, so then I am going to get a spiral, and not necessarily increasing. If it is decreasing also, I am going to get a spiral. Is it okay? Does that convince you?
Yes, sir.
Right? So for that, what I want d theta dt. I want d theta dt to be either strictly greater than 0 or strictly less than 0. I don't want it to be 0. Okay. So if I can prove this, then I can definitely tell that for complex values, complex eigenvalues with your non-zero real part, I am always going to what? Find a spiral. Okay, so I will try to do that, but I cannot guarantee you that I am very convincing. But still, I'll try my best. Let me see what comes out of that. Okay. Sorry about this. Okay, fine. So, how much time do I have? Okay, I think I'll have enough. So, okay. So, how Simmons has done that? See, if you consider any point, in the xy plane, and then in polar coordinates, simply x equal to r cos theta, y equal to r sin theta, right? So then your theta is tan inverse y by x. Is it okay? Right? So now, if I want to find out d theta dt from this expression, so firstly, what is going to happen? 1 by 1 plus y by x squared, right? Okay. So then again, d dt of this. Is it okay? Right? Then d dt of y by x. So d dt of y by x, that is simply x squared, then x dy dt and minus y dx dt. Is it okay with everybody? Is it okay with everybody?
Yes.
Right? So basically, what I try to do, I try to prove that either d theta dt is strictly greater than 0 or strictly less than 0. Okay, so that I am always going to get a spiral out of this. Okay, fine. So, and I am considering the situation when I have, complex eigenvalues. Complex, in fact, irrespective of, whether irrespective of whether you get a center, whether you get an elliptical path or not. Okay, so that also can be considered as a spiral. Say, for example, if I look at R, say a e to the power say b theta. So if b is equal to 0, then R is going to be equal to a. So this is always going to be a circle, isn't it? Right? Fine.
Yes.
So then it is going to be a closed path. Although it has come from the equation of the spiral, it is going to be a closed path. Okay. So under this category, I will be able to encompass all the complex roots. Okay. Fine. So then this is simply, say this is going to be x squared plus y squared, and then on the top, like numerator x squared will come. That will cancel out with this. Okay. So this will be simply Jiten. Okay. Now remember, my system of equations, I have taken it to be your this. Right? I have taken it to be something like this. So now, if I substitute it here, so then I am going to get, x dy dt, cx plus dy minus y, ax plus by, and that is going to give me, cx squared plus y squared. So then this is cx squared plus d minus axy and minus dy squared. Fine, minus dy squared. Okay, fine. See, since we are considering trajectories, since we are considering paths, we can easily assume that your this x squared plus y squared is not equal to 0. Because generally what we are going to do, we are going to take the initial point, to be non-zero, isn't it? We are going to consider the starting point as something different from the critical point 0, 0. Okay, so I can always make this assumption. Okay, so now another interesting fact is coming here. Okay. Okay, so if you recall, when we were trying to find out the eigenvalues, right? So the discriminant was given by this, right? Discriminant was given by this, tau square minus 4. Is it okay with everybody?
Yes, sir.
Fine,
Yes, sir.
it was given by this. And since my matrix was like A, B, C, D, then you know that this is A plus B whole square minus 4 into AD minus BC, right? Is it okay? Fine. So this is going to be A square plus B square plus 2AD. So if you take minus 4AD, this is going to give you A minus D whole square plus 4BC. 4BC. Okay, fine. Yes, so far so good.
Yes, sir.
Fine.
Yes, sir.
So now you remember that complex root occurs when the discriminant is strictly less than 0. Isn't it?
Yes.
Yes, sir.
Right? We are going to have complex eigenvalues when this is D is strictly less than 0. So since this part is already non-negative, so that means what must happen? This BC must be negative, right? BC must be negative. Is it okay?
Yes, sir.
Right? So that means B and C must be of opposite signs. B and C must be of opposite signs. Is it okay? Fine. Up to this, it is fine.
Yes, sir.
Fine. So that means now look at this expression. Look at the expression for d theta dt. See, I am trying to prove that basically this expression is either positive or negative, not zero. Okay. So then, since I have already found out that the signs of B and C are opposite to each other, what I can do? Let me assume that C greater than zero. C greater than zero. Okay. So now if C greater than 0, obviously you can see that, I mean, when y is 0 in this expression, if y equal to 0, then what is going to happen? Like d theta dt is simply going to be equal to C, and that is strictly greater than 0, right? Is it okay? Fine.
Yes. Yes.
Fine. Okay. So now let us assume that y is not equal to 0. Y is not equal to 0. Okay. So then what I can do? I can restructure this as okay. So okay, fine. Isn't it?
Yes.
Right? So now I have to prove that when C is strictly greater than 0, this d theta dt, this is strictly greater than 0. So for that, I have to first prove that your numerator is always non-zero, right? So now let us see what happens when the numerator is 0. So if the numerator is 0, so then what is going to happen? C this, if this is 0, because my x and y are real, right? Because my x and y are real. So if I solve it for xy, if I solve it for x by y, so then I must be able to find x by y as a real number. Is it okay? Fine.
Yes, sir.
If the numerator is 0 for a real x by y, so then what is going to happen? Your x by y, that is going to be what? Your d by a minus d by a plus minus root over d by a whole square minus 4bc, right? Is it minus or plus? Yeah, fine. And this is 2c. Okay, right? So now, what must happen? If xy to be real, this discriminant d here, I mean, of course, this is d squared.
Sir, right hand side is complex.
Okay, anyway, so this one, this d, d must be greater than 0, isn't it? If I am seeking a real x by y, the expressor under the radical sign, it must be greater than 0, isn't it?
Yes, sir.
Greater
Yes.
than or equal to 0. But because I am considering on the complex rule, I already know that this d is strictly less than 0, isn't it? That is not possible, right? Is it okay?
Yes, sir. Yes, sir.
Right? So
Yes, sir.
that is why d theta b is non-zero. Okay. So now let me tell you which part is I am not very comfortable with. So after that, Simons has concluded that. So that is why for c greater than 0, of course c greater than 0 is going to make this whole expression positive, right? Because b is negative, that this is positive, right? So he says that, so in that case, your d theta dt is going to be strictly greater than 0. And after that, he has commented that, I mean, d theta dt is strictly less than 0 when you assume c to be strictly less than 0. My only concern is that what is going to happen to this particular term? What is going to happen to this particular term? I am fine with the first and the third term when c is greater than 0. I know that they are going to be positive, but in order for the numerator to be positive, I want this one, right? Xy whole square minus b. I want this to be strictly greater than d minus a by xy, isn't it? Are you getting my point?
Yes.
Right? So you just try to find that out. I mean, I'm leaving it to you, but I'll still try to find the answer to that. Okay? So you try to find the answer to that. Why? If c is strictly greater than 0, is going to give me, I mean, this also, the numerator also to be greater than 0. Because we have already proved that this is not equal to 0. Okay? Alright, so similarly, c less than 0 is going to give me that to be negative, d theta dt be negative. Okay, so with that proof, I can say that since d theta dt is always increasing or decreasing, strictly increasing or decreasing, I'm always going to get a spiral from the system of equations, from the trajectories of the system of equations. Okay, right? So I think that's it for today. So as you are going to have exam on Saturday, so I'll try to upload one recording, and if I don't do that, I will see. If I do it, I'm going to inform you. If I don't do it, then you know that I didn't do it. Okay? So then I will see you on Tuesday. Monday I don't want to do the class because Monday I have some other engagements. So Yeah, so we'll see you